Hello everyone, my name is Viraj and today we'll be looking at the 17th problem from the CP-31 sheet by TLE Eliminators under the 800 rated questions. Let's go. So I'll be moving on to my 800 rated problems. I have to go to my 17th problem, forbidden integer. Alright, let's see this problem. You are given an integer n which you want to obtain. Now, you are given an unlimited supply of every integer from 1 to k except integer x, that is, there is no integer x at all. You are allowed to take arbitrarily any amount of each of these integers, possibly you can say 0. Can you make the sum of the taken integers equal to be n? If there are multiple answers, you can print any. Alright, so very simple problem to understand. Let's try to generalize this back and see what is given to us. So we are saying I have three variables, n, you have n, k and x. Now what do they denote? N is a variable which denotes a value that I want to make. Now k is another value which actually denotes, you can make it like this, k is a value which denotes that I have the numbers from 1 to k available with me in, you can say, unlimited supply. And x, what is x? X is the variable that is not present. So let's try to understand this example. If let's say I say n is equal to 5, k is equal to 4 and x is equal to 3. What does that mean is, I want to create a value 5. I have numbers from 1 to 4 available, but the number 3 is not present. As in, basically, if I said from 1 to k it's available, that is 1, 2, 3 and 4 were available in abundance, but because x's value was 3, 3 is actually not available in abundance. It's basically not available at all. And the numbers I have available is only 1, 2 and 4. Another question that I am asking, or the problem is asking to you, is there is no restriction on how do you make it. Multiple answers can be possible. Just give me yes or no. If you give me a yes, give me yes to this question, whether you feel that using any of number of times, any of the values that are possible for you to use from 1 to k except x, can you make a net sum equal to n? If that is yes, if you think that the case is yes, then you will print yes, and then you will have to print that set of numbers, you can say, which actually sum up to give n, or in this case 5. And if you think it's not possible, then you simply have to print no. You don't print anything beyond this. Alright, so this is the problem. Let's try to now take this case only and understand. Let's say for n equals to 5, k equals to 4, x equals to 3 was a case. One very simple case I can formulate for myself is, answer is yes, and the answer is yes. Why? Because I can take number like 1, 1, 1 and 2. Find the sum for this. 1 plus 1 plus 1 plus 2 is, of course, 5. So the sum is 5. I have used the numbers 1 and 2, which are in the given range, or are in the given set, not range anymore, given the set from 1 to k numbers except x, and I'm using them as many number of times as I want. Like I'm using 1 3 times and 2 1 times. Now I could have also written something like 1 2 2. This is also a viable answer. This also gives me sum equal to 5, and this would also have been accepted. That's why in the problem they have said that there can be multiple answers. If you feel the answer is yes and there are multiple possible answers, print any one of those answers, you'll be good to go. But only print no if you think no possible answer will satisfy this condition to create n from unlimited supply of numbers from 1 to k except the number x. Alright, so this is the whole problem. We have understood this with the test case also. Now let us try to picturize the time complexity. When I am looking at the constraints, what sort of a order of time complexity do I want to reach? Alright, so this is very important because I know I want to not create redundant ideas. I want to create ideas which actually run in a complexity that is within my constraints. So over here, I know for sure by fact that in 1 second, I am allowed 10 power 8 elementary operations. right? Now in this question, I have been allotted time limit per test as 2 seconds, which means 2 seconds would give you 2 into 10 power 8 elementary operations for running in per test. But every test has some test cases, and that test cases is denoted by T, which is maximum in 100 order. So if I ask you what's the number of operations you perform for every test case, you simply report that to be 2 into 10 power 8 upon T's value, maximum value is 100, so you can report this 100, which gives you 2 into 10 power 6 by simple mathematics. That means I have been allowed elementarily 2 into 10 power 6 operations per test case. Now this is very important because if I look over here at the constraints, that is x, k and n, all are maximum in 100 order, alright? So let's just assume for right now, like maybe the time complexity is dependent on x and k and n altogether, but just let's try to keep a very simple picture of when we are talking in terms of 100 order, right? When I'm talking in terms of something like 100 order, can I create a solution that runs in maybe, let's say, only dependent factor for right now was n. So if I talk about powers of n, can I create n cube? Yes, n cube will work. Why? Because n cube means I'm basically creating 100 cube, which means I'm creating 10 power 6 only. That's 10 power 2, whole power 6, whole power 3, that's 10 power 6. So I know this is going to work for n equals to 100 order. If I go above this, then I have a problem. n4 will not work. Now, if I go below this, will O of n square work? Yes, of course, because n cube works, then L square will of course have to work. So will O of n, so will till you create something like a constant time. So you know time complexities like this are going to make sense, but time complexities like this are a problem. So anywhere in an order where you exceed 10 power 6 order is a problem. Now if you create something like with x, k, n also as a time order, since everything is maximum in 100 order, I have just assumed that you are talking about degrees of 3. They could have been any combination of x, y and k, x, k and n in the time complexity parameters. That's not a problem for us. What we wanted to discuss was the idea so as to picturize what order do I want to go to a higher limit. Now it's not necessary I create an order that's in power 3, like something like n cube. Maybe I create a solution that's constant, maybe I create a solution that's log n. But I know if I want to create a solution and I want that to run, assuming my logic is right, it should not run above n square. And this is my expected time complexity discussion. Alright, expected time complexity discussion. Alright, great. So now we have discussed the sample case, we have read the problem, and we have also a nice idea so as to feel what sort of a solution do I want to create. Now let's come to the main part of discussing this problem. Now this problem by its very virtue looks like a very case-based problem, alright. Why is that happening? Because we can see there are a lot of different scenarios which we can create and different answers we can give to those specific scenarios. A very simple thing that points to my mind is, first of all, when questions look up, by experience I'm telling you this, when questions look up to have this multiple answer sort of a thing, you of course don't want to create multiple random answers for every question, for every answer. You want to generalize something, right? You want a solution that runs in most of the cases. That's why when we see problems like multiple answers, our mind should run towards creating a solution that's more general, more realistic, and covers large chunk of cases. All right. Now in this case, I have a very small bifurcation by intuition that comes into my picture. That is, I am talking about this number x, which is the number I cannot have. I have all the other numbers in abundance. I can use them as many times as I want. There is no restriction on how many numbers do I want to use, anything like that. I can have various set of combinations. This x is always a problem. Now, if this x is a problem, why am I saying this to be a problem is, I have a very simple intuitive idea. If I want to create a sum to be n, and I don't have any limit on the numbers I use, what's the very child-friendly sort of a solution you can report for you to create n? Very simple, I can say, I have the numbers from 1 to k, right? I have the numbers from 1 to k available with me. Right now, let's not picture about x. Okay, x is not in the game. 1 to k integers available, all in abundance. Why do I want to generalize my solution further? Because I know most cases will be covered very easily. And a very general solution when I have integers from 1 to k and I want to make a sum of n is simply you take ones. You take n number of ones. You can take 1 plus 1 plus 1 plus 1. So on, so on, so on. How many number of times? You can say n times. That's all, right? If you take 1 n number of times, will you not get the sum? Of course. And remember, is there any restriction on how many numbers do you use to create the sum? No, right? I just want a neat answer which works. Now this is very, very efficient, by the way. Why? Because all this is telling me is, irrespective of whatever n is given, it's 100, it's 10, it's 50, it's 49, it's any random number given to you, just create such ones, that many number of ones, and report that as your answer. That's the set of numbers that will give you a sum of n. So this is a very good case making or very intuitive sort of a solution, but the problem rises is this x comes into picture. We don't actually have the numbers from 1 to k. Remember, we have numbers from 1 to k except x. So this generalized solution which comes to my mind initially is going to lack on two cases which I can form from x now. Now this should come by intuition. Case number 1 would be x is not equal to 1. Let's say x is not equal to 1. That means basically you have the integers from 1 to k, but you don't have x. Now if you don't have x, if you don't have, you have integers from 1 to k and x is not equal to 1. That's the correct statement. X is not equal to 1. Now if x is not equal to 1, that means it's some other number, right? 2, 3, 4, 5. But do I bother? No, right? I have created a very generalized solution where I say, okay, 1 is available to you. Why not create n ones? Good to go. So the solution becomes very simple when I say x is not equal to 1. You can simply say, I will print n ones and the answer will be yes. Alright, so this is case number 1. Now, of course, because I have made this to be the case number 1, there is only left over second case where I say, what happens when x is equal to 1? Now, this is where things get more interesting. So, I'll repeat the idea again. First of all, I started with a general intuition that, okay, what's the child play problem generalized, method or whatever you can call that to create n? Just club up all n number ones, n times ones, that would give you the sum. But the problem was, you don't have integers from 1 to k, but rather 1 can be a number that's actually missing. That's actually the number x. So we made that into two cases. One case is, what if x is not equal to 1? Good to go. We can directly print a yes and just print n ones. Straightforward, that's a correct answer. And it's generalized, covers most of our cases when x is not equal to 1. I blindedly yes. But the next case becomes x is equal to 1. How do I take that into picture? So when we see that x is equal to 1, we can now start creating more cases. All right. Let's try to imagine this part. Now x is equal to 1. That means x as 1 is not available. So if your range is from 1 to k, basically you can say 1 is not available. So what's the next integer that comes into picture when we have to forward in our idea? Of course, this k value, right? X has been set. It's basically equal to 1. So it's now almost constant because the other way of when x was not equal to 1 has already been discussed. It's done and dusted. So when x is equal to 1, your next case variable that can be a variable, can twist your answers is k. So let's focus our energy on k. Now if x is equal to 1, 1 is not available. What if k is also equal to 1? What happens then? If k is equal to 1 and x is equal to 1, then basically x cannot be used. And the numbers from 1 to k were available. Now because k is 1, 1 to 1 or basically 1 was available and 1 was not also available because you said except x. So indirectly you have no integers available. You can say no integers available. And this is a very child's play to answer this question. If you don't have any integers available to use, then how will you create any sum, right? N is going to remain as it is. You will never be able to gather n as a sum. So this fetches a direct no case because this tells me you don't have any integers to start with. How will you create n? All right, good to go. So this becomes sort of like a sub case A over here. Now let's discuss more. What if k is equal to 2? What happens then? So basically you have integers available from 1 to 2 except 1. That means you only have 2 available. Now if you only have, I'll write this down, you only have 2 available. Now imagine this very simply. You have only the number 2 available in abundance. You, let's say, keep on adding 2. 2 plus 2 plus 2 plus 2 plus 2 plus 2 plus 2. What's a very simple virtue or the property of the number you achieve when you have taken a summation of a lot of 2's? It's a very simple thing to observe, right? The number you achieve finally has to be even. Because if you keep on adding 2's, 2 plus 2, 4, 4 plus 2, 6, 6 plus 8, to 8, then 10, then 12, then 14. What's the property? Because you're adding 2's continuously, you achieve a number that's even. If you achieve a number, or if you can achieve a number which is actually even, but you want to achieve n, it automatically tells me new yes and no cases. Very, very important. What new yes and no cases? Those cases are, let's say n was even. Then what can you simply do? I can print n by 2 number of times 2's. How does that make sense? If let's say n is 8, assumably, you can print 4 2's. That is 8 by 2, 4 2's. 2 plus 2 plus 2 plus 2. You get a sum of 8. Let's say you have 16 n as. Then you can do 16 by 2. You can print 8 2's. You will print 2 plus 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 2. That gives you 16 as a sum. So very, very easy mathematics to understand. If I want n as a sum and I only want it to be made up of 2's, it should be even. And if it's even, I get an answer yes, and I can print n by 2 number of 2's. But what happens when n is odd? What happened n was odd? This is a problem, right? You were limited that k was 2, which limited you to only have the number 2 in abundance, because x equal to 1 was already there. So 1 was never available. Now, if 2 was only available, 2 was only in abundance, can you create an odd number? Is it possible for you to sum up 2's and 2's and 2's and create an odd? No, right? Because if you keep on adding 2 to some initial limit, starts with 0 as a sum, you will never get an odd number. That's the property of how 2's and even numbers are going to get handled. It's a very commonsensical thing. No need to prove that part. I know this is automatically a no. I will never create n as odd if I keep on adding 2's, because 2's makes even numbers only when we add. It's 4, 6, 8, 10, so on. Very simple. Do this on a pen and paper, you will understand. We can only get an even sum. I cannot get odd sum. So n is odd, direct no answer. Alright, so you can call this as our sub case B or something. Now let's move even ahead. So we discussed K1, we discussed K2. Now we should, of course, like by logic, we should go for K equals to 3. So what happens now? Now since K equals to 3 is there, you basically have 2 also available. You basically have 3 also available. Now if you have 2 and 3 both available, what are you looking at? Since over here, you are looking at the same case getting repeated. If let's say n is even, then do I need to consider 3 or maybe more coming numbers? No, right? Our analogy was sorted. If n was even, you have to print 2's. You'll be good to go. But what happens when we talk about n odd? N odd failed when k was 2. Remember, when k was 2, n odd failed, because if k is 2, you only have 2 available. You don't have any other possibilities available. So you know n odd will give you a no. But what about when we say that k is equal to 3? So basically you have 2 and 3 available. Now if that is the case, you know for short that n has to be greater than equal to 3. I'll write this down. N has to be greater than equal to 3. Now try to understand this why. When I say it's greater than equal to 3, basically I say n is not 2, right? So why am I saying this? Is of course, right? You are, like one case is obviously done when n is even. Same case repeated. You can say answer is yes. And you print n by 2 2's. Alright, this is the yes case. Now we're talking about the odd part. What if n is odd? This case was direct a no in the previous one when k was 2. But now that you have higher range of numbers, like more distinct numbers available in unlimited supply to use, broadly in this case 2 and 3. Let's try to imagine in this case when n is odd, either n is like 1, 3, 5, 7, all these numbers. But is n ever 1? N is never 1, right? Why? Because if you carefully observe over here, I think you must have missed this condition. N is greater than equal to k is greater than equal to x. This is very, very important. So over here when we come back, we said k is equal to 3. So if k is equal to 3 and n has to be greater than equal to k, then can n ever be 1? N can never be 1, right? And if n has to be odd, n cannot be 1. So n of course is going to start with 3 and it's going to have 3, 5, 7, 9 and so on values only. So if n is odd, the only set it contains is 3, 5, 7, 9, so on, so on, so on, to a very high limit, maybe like to exactly how much, whatever we can cover it, odd numbers till the 100 range. That is all it's going to have. And in this case, now the answer is yes. It's not no anymore for k equals to 2. Why? Because very smartly, I have a small case making over here also. What I can do is, let's say you have n equals to 3. Just print 1, 3. Are you good to go? Can you print a 3? Of course, because I have k as 3, so I was available with 2 and 3 and unlimited supply, so I printed a 3. What about 5? I can print a 3 and a 2. Good to go. What about 7? I can print a 3 and a 2 and a 2. What about 9? I can print a 3, a 2, a 2 and a 2. What about the next number? It would have been 11. I could have printed a 3, 2, 2, 2, 2. Can you get the logic? Can you get the pattern? Yes, I think it's pretty observable. If let's say I find n as odd, what do I want to do? I want to print that 1, 3 and then rest over times I want to print 2, because we just discussed it's going to help me gain a odd n sum. So to get that into picture, how can I do that by mathematics? I can simply say that I want n minus 3 by 2 number of 2's, and then I want that extra 1, 3. That's all. And this is going to get me the correct answer. So basically, I get yes in both these cases. I just have to make 2 sub cases in that also. You can call this like something like a C1 case and a C2 case, so that I know that although I'm printing yes both times, but in even case I'm printing n by 2 2's, but in odd case I'm printing n minus 3 by 2 2's, because from n I will subtract that 3 which I want to print extra, and I will print that at the very end. I'll print just that 1 extra 3, because that tells me for covering n as odd, being n greater than equal to 3, I would have gained something like a 3 then some 2's, 3 then some 2's sort of a solution for all odd numbers greater than equal to 3. Alright, and now we can even further generalize this case, because I don't want to create something like k equals to 4, k equals to 5, k equals to 6, because if you observe very carefully, we have covered everything, right? Look over here. When we started with case A, where k equal to 1 was there, you had a no situation. When you said k equal to 2, you had a yes no situation. So you were still having some cases left out. But when you reached k equals to 3, you found that for any sort of n possible, either even or odd, by its virtue, you are creating the right answer. You are getting yes in all sorts of cases. So do I need to expand any further? Do I need to make go also a discussion for k equals to 4, k equals to 5? No, right? When I discussed in the very end start of the problem that multiple answer sort of a solution is always generalized better. And if you create a generalized solution or target a generalized solution, you come up with your approach much quicker. And this is what we did over here. Although we started with k equals to 1, maybe you could have thought we went till k equals to 50, or we could have had a long discussion. But when we went to k equals to 3, we saw that, yeah, we were able to cover all possible sets. And this is when we can stop. Now k equals to 4, 5, all are useless for me, because I can just portray my ideas of k2 and k3 and k1, everything combined to cover all cases. Alright, so this is a very, very fun problem. It's kind of a very case working problem, not the general problem on how you would have solved with some mathematics or something. It's kind of an ad hoc problem where you create some solutions, create a lot of cases, and this has to jump up in the right place so as to create what sort of cases in bifurcations I could have done with respect to x and k. And by idea, I was able to see that, okay, x was divided in not one case, and then k was my most bothered variable now, so why not divide it in 1, 2 and 3, and as soon as I reach 3, got all yes, can close my chapter over here, I will get a right answer. Alright, so now let's jump to the code part and understand how can we implement this out. So very, very simple. I'll take n, k and x over here. Now you will see a lot of if and else checks, so the code might look a bit tedious in front, but then we have quickly discussed all the cases. So as we go along with these cases, things will become simple. So we'll go to a very simple one test case when we said x was not equal to 1. This is our whole story when we started. We simply said if x is not equal to 1, I would have printed a yes. Then I would have printed those n numbers. So I'll print n over here, because we were also required to print the size of the numbers set we total print. So I want to print n numbers, and what those numbers should look like, basically all ones. So I'll run a loop from 1 to n, very simple thing to do, and print ones, and then finally change your line after leaving after every one. So this is simply basically printing ones in a single line so that you're able to report your correct answer. So this handles our case 1 which we discussed over here. Now we went to case 2 when we said what if x was equal to 1. So then we had like 3 subsections. Now what I did over here is, to make my code even more clean, I combined some cases. We know that if k equal to 1 is there, that is when no integers are available, so that you never create n, or when k equals to 2 is there but n was odd. In these two cases, you are getting no. So why not combine them both? What I have done over here is I said, okay, if k is equal to 1, or then you can see I have a major bracket opening inside which I have two conditions put in and together. Those conditions are k was 2 and n's nature was odd. So either these two conditions together become true and this gives me this no case which we discussed over here, or the only one condition that k was 1 becomes true and this condition gives rise to this no integers available condition. In these two conditions, I blindly you have to print a no. Else you can print a yes. You can of course you print a yes. Either you are in this case or we move on to the next set of cases when k was 3. You have to print a yes. So why not print a yes line over here simply, and now do a simple check. This check extends and now I know if n mod 2 is equal to 0, that is if n is even, what do I want to do? Even in this case over here when n was even, I was printing n by 2 times 2's. And even in this case when n was even, I was basically printing n by a number of 2's. So I don't need to bother myself with this case over here. This is kind of like, you can say, a redundant case for me, right? This is a redundant case for me. I don't need to bother this case, and I can simply move on to say, irrespective of whether n is whether k was given 2, 3 or even more values, n being even straightforwardly tells me I want to print n by 2 2's. So I'll print n by 2 as my set count, total number of numbers I want to print, that is n by 2, and I'll run a loop from 1 to n by 2 and simply print 2's, and then I'll change the line. If I go in the else block, now I know I have actually gone into a condition when n was odd. Now if n was odd, case over here was already tackled, right? There's no case in this situation was already tackled because you have involved this in the upper if else check. So now when you have entered the else block, you know for sure that you are talking about k being equal to 3 or more, and now answer is yes, but it's a bit tricky. How do I want to print it? I want n minus 3 by 2 number times of 2's and then 1 extra 3. Effectively, how many numbers do I want to print? I want to print n minus 3 by 2 plus 1 numbers, and I'll run a loop from 1 to n minus 3 by 2. I'll print some 2's, then I'll print a final 3 and I'll come out of my logic. Alright, so my code is actually an implementation difference. If you pause the video, you have understood the idea, you can implement this code in 10 different ways. Alright, as long as your idea is correct, as long as you're able to clearly picturize in which if and else checks you are handling, which if and else conditions, as you make your cases on your own, your problem will work, you will get an accepted solution. And this is what I'm getting over here. Alright, so now what about my discussion for time complexity? I have a very basic time complexity over here. I'm taking inputs. So this is up till here, all I'm doing is taking inputs. Then I have simple checks that start off with a constant check that if x is 1 or not. But inside that, when I finally get to the point where I want to print an answer, I'm doing a looping to do that basic outputting of 1's or 2's or 3's, whatever I wanted to print at locations. So one loop is over here also n, and in this case also somewhere or the other I'm running a loop. This is like an n by 2 order. Effectively it's n order only because you don't consider the factor. This is also sort of an n order only because n minus 3 by 2 is not considered to be n minus 3 by 2 operations. It's an order of n operations only. That means effectively if I talk about time complexity, your time complexity stands out to be O of n, which is actually very, very nice because I had n basically going in 100 order. So I can call this as O of 100, and this is good to go. We discussed something like a 10 part 6 boundary and we have only received only a 100 operation count per test case. And what about space? I'm not using any extra space, so I can call this as constant because I have not taken any extra data types, in data structures to be specific, any array or anything like that. I have constant variables, everything is calculated in constant time, single variable space don't count. So it's basically constant space, good to go, my logic is correct, I will not get a TLE. Alright, so this is a very casework sort of a problem. It requires, first of all, how you sit with your pen and copy, you make 10-12 cases on your own, and you bifurcate the understanding of where x is not 1 is a case, where x is 1 is a case, and inside that, how do you make more cases. Alright, so I hope you like the video. Thank you for watching.